to do. All right, good. What's up? Yeah, hurry up, go. Yeah.
Hello, people.
That was great. All right. So you had like a bajillion problems to do. Let's go over like 5 of them.
Let's go over. Can we do 23?
Because most of them were pretty easy, I thought. Yeah.
Yeah. Can we do number 36?
Yeah. All right. So wait. Good. Section. Yeah. Section 9.1 was all about like it was like pretty straightforward, I think, right? It just like taught you about summation notation, assuming you didn't know it already, and talked about a sequence. It was like all just kind of stuff that was like obvious. And then you had to do some math. Oh, it also taught you what the factorial symbol means in case you never learned that before. Let's do like 3 or 4 of these. What are the like ones that are like most fun?
23, 32, 36, and something else.
Say that again.
23, 32, 36, and something else.
What's something else mean?
I don't know. I only had 3 circles.
Interesting. Okay, good.
That's
All
all
right.
you need.
Good. So 23. Oh wait, did I also assign this crazy problem 69, right?
Yeah.
About the Fibonacci sequence?
You can do some. That's not hard.
Good. Ryan, erase the board. 23 says simplify the ratio of factorials. Yeah. So that's 2n minus 1 factorial over 2n plus 1 factorial. Okay, well, what is a factorial after all? We learned this in the section, if you didn't know it already. 5 factorial means like 5 times 4 times 3 times 2 times 1 all the way down like that, yeah?
Yeah.
Okay, so 2n plus 1 factorial. What is 2n plus 1 factorial? It's just 2n plus 1 times 2n, right? Times 2n minus 1, etc., all the way down. Which could just be written as 2n minus 1 factorial. And then you have 2n minus 1 factorial on the top too, get it?
Oh, that's magic. I didn't wait to do this.
What is your weird?
I wrote a bunch of stuff.
Okay, good, say good. Okay, that was 23. 32. What the hell is this? Write an expression for the most apparent nth term of this sequence we give them. Oh, okay, so this is just like straight up pattern recognition, right?
Yeah.
1 plus a half, comma, 1, stop talking, 1 plus 3/4, 1 plus 7/8, etc., 1 plus 15/16. Alright, I mean, there's a lot of different ways to do this, but I guess the most obvious pattern is that it's always just like 1 plus.
X minus 1 over X, and then X is 1.
Yeah, that's one way of doing it, right? The bottom is always a power of 2.
Yeah.
So the bottom is always like 2 to the n,
Yeah.
and the top is always 2 to the n minus 1. I'll take that. Okay. You could, yeah, that's good enough. All right, good. 36 was a similar kind of a thing. Find the pattern. So this is just like 1, 2, 2 squared over 2, 2 cubed over 6, 2 to the 4th over 24, 2 to the 5th over 120. Well, I recognize those numbers on the bottom just very clearly. They are the factorials, right? So this is 1, this is 1. So what is this? This is just going to be 2 to the, we have to be a little bit careful though. It's going to be 2 to the n minus 1 over n factorial. I think that's right.
N minus 1
I didn't get the bottom part of that. Makes sense.
N minus 1 factorial.
Yeah.
N minus 1
N
factorial.
starts at 1.
Because you can
Why?
prove that 0 factorial.
No, it's 2 to the n. That's
How are
right.
you going to do
Because
that?
3 times 2 times 1 is 6.
No, but I think that's the right pattern because if you start counting with 1, which is they say to do that.
Oh, okay.
If you start counting with 1, then the first number in the
0
list.
factorial is 1.
0 factorial is 1. Yeah, more on that
that was in
later.
the-
But yeah, if you plug in 1 for n, then you get 2 to the 0 over 0 over 1. So it's just 1.
Okay.
If you plug in 1 for n, now you get.
No, you're right.
Then you get. Oh, I did that already. Sorry. If you plug 2 for n, then you get 2 over 1. So that's all. That's good. Yeah, good. Okay. All right. This problem I thought was like really awesome actually, and had like a lot more going on than you might have thought. So this problem said, okay, first of all, it introduces you to the Fibonacci sequence in case you have never heard of it before, but we talked about it in class. So the Fibonacci sequence is the one which takes the sum of the two previous terms, yeah? And of course the first two terms are 1. Okay. Well, and part A says, yo, just write out the first 12 terms of the Fibonacci sequence. Make sure I'm in frame, quick.
Yeah.
So it's like 1, 1, and then you go like 2, 3, 5, 8, 13, 21, 34, 55, tell me when I can stop, 89, 144, and good. Good. Okay, now, in section B of this wonderful, amazing problem, it introduces you to a new sequence. Watch this. It says, consider the following sequence, B sub n. B sub n is the ratio between a term of the Fibonacci sequence and the previous term of the Fibonacci sequence. Cool?
Yeah.
Okay, and it says for n greater than 1, but I reject that. I think we should start counting at 1. Okay. Write out the first 10 terms of this sequence. Surely, I will do so.
Wait, sorry, what did you reject?
I think we should start with n being 1, because it works, right?
Yeah, it works.
Wait, what did it tell you to start?
I told you to start n bigger than 1, but I thought that was silly. Anyway, okay, so basically you do the ratio between this term and the previous term, so that's like 1.
Yeah.
And then the next one would be 2, and then 3 halves, and then 5 thirds, 8 fifths, etc., 13 eighths. Can I stop at a certain point? Depends on your board. 21 13ths, and so on. Okay, good. Now some actual math.
No, not really.
Using the definition in part B, prove a sort of identity, prove a like recursive rule for this B sequence. So we were supposed to do a proof that B sub n is in fact 1 plus 1 over B sub n minus 1. Okay, why is this so? Well, I don't know. What should we do?
Start with the definition.
n minus 1 equals a n minus 1 plus 1.
Do that later.
A n minus 1.
Okay, I think Matthew is suggesting that we start on the right-hand side, because when proving an identity, that's like pretty much what you do, right? You start with one of the sides and show that it goes to like the other side. Okay, so he begins his proof with the expression 1 plus 1 over b sub n minus 1, and he's going to attempt to show that this is b sub n. Cool?
Yeah.
Okay, what is b sub n minus 1? Well, by the definition of the b sequence, b sub n is like the ratio between like the next term in the Fibonacci sequence and like this one, or something like that, right? So b sub n minus 1 would be 1 over, like I guess it would be like b sub n over, or sorry, a sub n over a sub n minus 1. I think if I did that right.
Yeah.
Okay, so that just is the definition of b sub n minus 1. And then we do advanced fractions. This is 1 plus a sub n minus 1 over a sub n.
And then
And then we get a common denominator. So this is a sub n plus a sub n minus 1 over a sub n. Yeah? Is this what you guys mostly did? And then what is a sub n plus a sub n minus 1? It just is a sub n plus 1 by the definition of the Fibonacci sequence. That's how you generate the next term of the Fibonacci sequence, the sum of the two previous. And this is, by definition, b sub n. So I kind of just like zoomed it all out. Yeah? Alright, so that's like cool and stuff, but I think the like, is there like a bad glare?
looks fine.
When you're in class live, you can just like move your head, but when you're home on video, it doesn't that trick doesn't work.
Her space is blocking out part of the board.
Guys,
There's
if you're
a glare on
having
the
issues
video.
with Blair, yell now.
Alright, good. Alright, so what makes this so awesome? Well, what this is telling me, this is actually telling me a sort of a deep, wait, shh. This formula is giving me some deep telling me something. It's telling me that, yo, if you want to find the next term in this sequence, then follow this rule. Okay, let's just check this rule to see if it works. What's the first term of the p sequence? Well, it's 1. How do I get the next term of the p sequence? Well, basically, reciprocate, add 1. Right? So if you reciprocate 1, you get 1, and you add 1, and then you get 2.
Yep.
Alright, then this rule again says if you want the next term of the sequence, reciprocate and add 1. So if you reciprocate 2, you get 1/2, and you add 1, you get 3/2. If you reciprocate 3/2, you get 2/3, and 1, you get 5/3. Alright, now I'm getting tired of like doing this, so Chelsea, you need the calculator remote control out of the top right controller and turn it on.
Turn that over there.
Yeah. Ooh. Good. So now I'll do something very fancy. I'll just like do this on my calculator. So.
Should we turn it off?
Did you turn the calculator? Yeah, it's on. Okay, good. So I'm gonna type like
Mr.
1.
Rose, your camera doesn't go high enough.
Oh, it does.
Yeah, but like
just
which
like
part?
just go
Towards the
go
tree.
what's that called? Go
Back?
handheld. No. Unsnap it
Put
and
it on
just.
June's desk.
What? You got this. You got this. This is high production values here. All right. Okay. So anyway, you just do 1 enter, and now what am I gonna do? How do I do stuff recursively? I just like do it, right? 1 plus. So it's like 1 plus 1 over like the previous one, yeah?
Yeah.
And if I just hit enter, then that's like 2. But then I can just keep hitting enter because when you enter, it just like repeats it, right? But it dumps the new variable into answer. So now I get 3/2, and now I get 5/3, and now I can just keep happily pushing buttons for a really long time, and then oh, something is happening. What is happening? Yes, I heard someone say like a C word.
Wait, why is he going down now?
Because it's approaching.
Eventually,
The computer's
something
getting busy.
appears to be happening. What's happening?
It's approaching 1.618.
It's approaching some kind of number. And actually now, the more I keep hitting enter, it's like no longer going to change it, right? I've exhausted the number of decimal places on my calculator. So what that means is that this sequence is approaching a particular number. It's getting closer and closer to some particular. What is that number? Do you recognize that number?
1.618.
That is the golden ratio. Okay, flip that back on. Do you know how?
Nope.
That is the golden ratio. Alright, we have learned something crazy. What we have learned is that if you continue this B sequence out forever, you get phi, the golden ratio. Alright, depending on what kind of middle school you went to, you may or may not know anything about phi, the golden ratio, but let's do a very quick recap. The golden ratio was probably taught to you once upon a time as like there's this like golden rectangle thing. And what is a golden rectangle? A golden rectangle is a rectangle in a golden rectangle is a rectangle in which if you cut a square off of it, then what remains is also a golden rectangle. Okay. Yeah, so if we let this x be, if we just call this like x and we call this like 1, which is like allowed, then ultimately I would like to find out what is the ratio between the sides in a golden rectangle. Well, I know that this rectangle is similar to the original rectangle, or it's supposed to be, so I know that the long side is to the short side, so x plus 1 over x, as the long side is to the short side, yeah?
Yeah.
Okay, and whatever x value is the solution to this equation will be that will be the answer. Okay, so you just do this, you get x squared equals x plus 1, so that's like negative x minus 1, and then you can just, doesn't factor, so you quadratic formula. Someone cool?
Yes.
Raise your hand if you've like done this before, like you learned this in middle school. Oh, like no one. Did they take this out of the curriculum?
Yeah, probably.
So
Probably.
none of you have ever heard this before?
I've heard of it.
I have no idea what it
You've heard of it?
I mean, kind of, but we didn't.
All right. Well, anyway, we're doing it. Okay, so solve this quadratic equation, please. Glad they took this out and added in doing conics poorly.
Weird stuff.
Like, it wasn't that bad, I just don't remember anything from it, that's the problem. Which I guess is a problem.
Alright, so x is like 1 minus the square root of b squared minus 4 a c. Alright. Did you guys get x equal, right? So did you guys get 1 plus or minus root 5 over 2? Yeah, and root 5 is like about 2-ish plus a little bit more. So the negative one I reject as just being like nonsense because like, you know, it's geometry. Okay, so the answer to this geometry problem is that x is 1 plus root 5 over 2. And that's kind of nice. And that is this number we call phi. And because the way I set this up is in the ratio like x to 1, I haven't just found x, I've actually found like
All of them.
all of them, because this is the ratio between the long side and the short side of any golden rectangle. Cool?
Wait, so how do you draw the tree? Is that just like a fourth?
No, it doesn't connect. It doesn't connect.
Like, how does it, like? Yeah, whatever.
Look at that. Okay, good.
It doesn't connect.
Okay, whoa. Okay, alright, good. Why is the golden ratio so great? Well, it comes up like all the time, man. In particular, it's coming up now. For some weird reason, so the golden ratio, yeah, okay. So this also, when you want to do like the cosine of like pi over 5, something which is something you want to do all the time, then then you need this. I'll just write like need this. In fact, if you want to do, every person in their lifetime should, by hand on their own without any help from anyone else, find the volume of an icosahedron.
What?
Which is quite hard. I did it last summer. If you follow me on Twitter, you know all about this. And heavy use of the fact that the cosine of pi over 5 is related to phi in order to construct a regular pentagon. All right, but back on track. What are we doing here? What we have just noticed is that this sequence has what we might call a limit, and the limit of this sequence is like the number that this sequence, the terms in the sequence appear to be getting really, really close to. And why should this be phi?
Stone cold silence.
Oh, should we talk a little bit more about phi, maybe? I think I have a couple more important things to say about phi. In particular, this is the geometric definition of phi, but it also has an algebraic characterization. Phi is the unique number which, when squared, is 1 more than itself.
How interesting.
Which it's fun to do this on the calculator, just because it's just like cute.
Do you want this film too?
Yeah, probably, right? Just like tilt the thing back. So if you go 1 plus root 5, oops.
This works too.
Close
I'm
over
too
2 like
lazy
that.
for this.
Yeah.
Like,
Did I do that right?
you could
No.
legit put it on June's desk.
No, thank you.
Is there no fee symbol?
I mean, I'm about to make one if there's one already. Boom, there it is. Okay, good. Let's like store that as like, you know, P for phi. Okay, so anyway, there it is, right? Well, if I square this.
Is there no button, like, for me?
Alright, usually people are impressed by that. Alright, maybe not. Alright, wait, don't go away. Wait, stop asking about buttons. Alright, good. And another property that phi has, you can divide both sides of this equation by phi, and it is also true that phi is 1 plus 1 over phi.
Wow.
In other words, yeah, phi is the unique number, which is 1 more than its own reciprocal. And also, 1 more, wait, I did something wrong. No, I didn't. Yeah, phi is 1 more than its own reciprocal, and 1 less than its own square. Yeah.
Wow.
Yeah, and of course this comes just right from here, right? I mean, phi is the solution to this equation. So that's why it has that property because it satisfies that equation. Okay, well, Hirsch figured something out. He's like, huh, I think I've seen this before. This one more than your own reciprocal. That's this B sub n sequence, right? The recursive rule for this B sub n sequence is reciprocate and add 1. Reciprocate, add 1, reciprocate, add 1, etc. So if you think about what's going on here, we could almost like make a giant, okay, let's see, how do I do this? So start with 1. How should I begin? Okay, watch, here's what we can do. We'll now do this in 2 different ways. First, so phi is 1 plus 1 over phi, right? So, but because phi is 1 plus 1 over phi, we can now do some phi-ception. So phi could also be written as 1 plus 1 over.
Oh no. Oh, put that in.
1 plus 1 over phi. And that could also be written as 1 plus 1 over 1 plus 1 over 1 plus 1 over phi.
Yeah.
Or that could also be written as 1 plus 1 over 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 1 plus 1 over. Alright, this is all phi. This is called a what's that called? Crap. No, it's got a name. I'm blanking. No, it's called a oh my god. What the hell is it called? Oh boy. Anyway, there's a name for this. It's called a something fraction. I'm blanking. I'll think of it in a second.
Can we just call it Dave?
No. Okay. Yeah. All right. Good. Good. Wait. On task. So how is that relevant to my sequence? Well, because, look, think about what you're doing when you're doing this sequence, right? You're starting with the number 1, and then how do I get the next element in this sequence? Reciprocate, add 1, right? So, reciprocate, add 1. How do I get the next element in the sequence? Reciprocate, add 1. How do I get the next element in the sequence? Reciprocate, add 1. Etc., 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 etc. So, as you go farther and farther out in this sequence, you are like building this sort of infinite, what the hell is it called? It's called a continued fraction. It's called a continued fraction. And this is the continued fraction expansion of phi. All right, how are we feeling? Good? That was like fun.
Mr. Rose,
What's up?
is there anything special about 1 minus root 5 over here?
Yeah, it's maybe it's like -1 over phi or something. It has some other property, but not really. It's not that important. It's related to. All right, good. What time is it? It's like the real time, right?
Yeah.
Yes.
Yeah, I set my clock back to be real. It's 2 minutes.
2 minutes ahead.
Let's call that real time. Okay, good. Let's go over some problems from the other section. I guess that's all we're doing today.
Can I do number 64?
I promised we'd learn new things, but that was, I guess, it's not. 64?
I'm sure they're glad we went over the homework, right?
Yeah, sure. How are you going to get there?
I feel like I should probably move this. Carl, it's so much effort.
Alright, let's do a couple of Hey, on task, what's wrong?
It's like you can actually see it.
But Carl's head is left.
Alright, good. Let's go over a couple of these. Which ones should we do? Let's do like, okay, that's the only one?
Yeah.
70.
Move it if it needs to be moved.
64, 71.
Even more
Alright,
heads in the
good.
way.
64 says, insert
further
k
back.
arithmetic means between the given
What should I
pair
do?
of numbers.
Here, guys.
Okay, so
What, on the table?
I have 2 5, and I want to insert.
I feel like someone should hold it.
Insert 4 arithmetic means. What does it mean to insert 4 arithmetic means? Well, I mean, what that. Okay, well, first of all, what is an arithmetic mean? Yeah.
Something equidistant between 2 other things.
Yeah. Well, okay, sure. It's like if you have 2 numbers, finding the arithmetic mean of those two numbers means finding the number in the middle of an arithmetic sequence. So what is the number that, the x is the arithmetic mean of a and b if a, x, b forms an arithmetic sequence. And the definition of arithmetic sequence is that the differences are common. So x minus a has to be b minus x in order for the sequence to be arithmetic, yeah?
Yeah.
And then when you just like do it, you get 2x equals a plus b, and so x is a plus b. Alright, it's just the average, but it's the average, it's the arithmetic average, it's the arithmetic mean. Okay, if they want to insert 4 arithmetic means, then they're just like, yo, like basically do this. That was the task. But find 4 numbers in between 2 and 5 such that this whole thing is an arithmetic sequence. Cool? So how many times have I added d in order to get from 2 to 5? I think 5 times, right? 1, 2, 3, 4, 5. Alright, so 2 plus 5d has to be 5. So that tells me what d is. 5d is 3, and then like just d is 3/5, yeah?
Yeah.
So those numbers are, whatever it is, 13 fifths, 16 fifths, 19 fifths, 22 fifths, eventually get to 25 fifths. Cool?
Cool.
Okay, good. Last one is this brick problem. 71, brick pattern.
Just 10 times 47.
Here's what it says. I will redraw all the bricks on the board just really quick. Just kidding.
No.
A brick patio is roughly in the shape of a trapezoid.
The MCQ is 47.
And the patio has 20 rows of bricks. Stop talking. 20 rows of bricks. The first row has 14 bricks, and the 20th row has 33 bricks. How many bricks are in the patio all together? Okay, well, this is, how should we do this? I guess there's a bunch of ways.
20 divided by
So essentially what we have here is an arithmetic sequence in which the first number of the arithmetic sequence is 14, and we go, just a bunch of these, and by the time we get to the 20th term, we're at 33. Yeah?
Yeah.
Okay. So this is the 20th term. All right. So I guess kind of like personally to me, the easiest way to do this is find what d is. Well, the 20th term of any arithmetic sequence is just the first term plus 19 of these constant differences. Yeah. Okay. So if the 20th term is 33, then I must have taken 14 and I must have added whatever the common difference is 19 times. Agree?
Yes.
Okay, and then this is just boring, right? D is just 1.
Yeah.
Yeah. Okay, so really, this is just telling me to add up the numbers between 14 and 33, right?
Yeah.
Okay, so I need to add up 14 plus 15 plus 16 all the way up to 33. And I can think of 2 ways to do this. I guess the easiest way is to just use the formula, right?
Yeah.
So the formula says, how do I find the sum of 20 terms of an arithmetic sequence? This is what we did on Monday. Well, I do the number of terms, well, I'll just do it, write it in general first. The sum of the first n terms is n over 2 times 2 times the first term plus n minus 1 d. That's just like the general formula that we derived for the sum of the first n terms of a sequence, yeah? Okay, so if I want the first 20 terms, then it's like 20 over 2, twice of 14 plus 19 of these d's, but d is just 1. And so that is 28, 19 is 47, so that's 10 times 47, so that's 470. Is that what you guys got?
Yes. Yeah.
Okay, good. Can I have this bookwork? I guess should we say goodbye to period 3?
Bye-bye.
Bye period 3.
They want to